In this video, I'd like to reiterate the applications of vectors, and for this series of examples, we're taking examples from our physics textbook. So for those of you that are taking physics right now, all of these are coming from, I believe, Chapter 4. For those of you not in physics class, you're of course welcome to participate in today's examples, but I also will have another video prepared in which we use examples from our trigonometry textbook. Look for that in a separate link. Now with this particular example, a ship set sail from Rotterdam in the Netherlands, and it's headed due north at 7 meters per second relative to the water. The local ocean current is 1.5 meters per second in a direction of 40 degrees north of east. And so what we would like to find is the velocity of the ship relative to the Earth. So essentially it's combined velocity. So one of the first things that I'll do is I'll change this 40-degree angle if necessary. Now 40 degrees is pointing north of east, and in actuality, if east is pointing this direction and north is pointing this direction, 40 degrees north of east puts it right here at the 40-degree mark, and on our 360-degree scale, that's completely fine. That is appropriate. In this first example, though, here in this first vector, we're being told that we're headed due north. And so I want to make note that that value due north is going to be a 90-degree angle when we use our component computations. Since it appears that our other three values were reported with 3 significant figures, I'll go ahead and do so with this one as well. So I'm going to sketch a picture first, and then we'll use the component notation in the calculator to identify the solution. So what I'm going to do is I'm going to draw a vector that's 7 units in length and is headed 90 degrees. Now I'll just use one grid line per meter per second. So there we go. There's a 7.0 meters per second at 90 degrees north. Now the challenge here is to determine where 40 degrees is. I know that 45 is, perfectly diagonal to the grid lines. So 40 must be some portion lower than that. And then the other challenge is, how do I indicate a line that's 1.5 units long at this diagonal? I can't really rely on the grid lines here. So I'm just going to make my best estimate. I'm going to say that 1.5 units at a 40-degree angle might be this vector here. So we now have the two components. Clearly the ship is receiving some assistance by the water or the ocean current pushing in this direction, and we can visually see that because the length of the blue arrow, the resultant of the sum of those two, is longer than the original ship's vector. But it is off course just a little bit, and so we would like to know what direction it's heading as well. So the question becomes, what's the velocity? That's the length of the vector. And it doesn't hurt to find the angle measure for practice as well, so we'll call that theta. And while there are a variety of methods that we can use to solve this, I think I'm going to show one method and try to remain consistent with it for this section of class, and that's going to be the component method. The component method from our notes last week looked something like this, that if I had the magnitude of a vector, I could multiply it by cosine theta and sine theta. This vector now, this unit vector if you will, is reported in this matrix notation. And after multiplying the magnitude times the cosine and sine of the angle measure, what we'll end up with is a vector whose components are indicated both in the horizontal and vertical form. And if I had several vectors, then I could now add those together, because this vector is in component form, another one would show up in component form, etc. We can then combine those. And that's precisely what I'll do here. The vector of the ship, and I'll use the letter S for this, and the vector of the ocean, I'll use W for water instead of O. Those two must be added together, and so the magnitude of the ship times the cosine of its angle, and and sine of its angle will be added with the magnitude of the water times, I shouldn't use a dot here for consistency, and you'll see why as we get a little bit farther along this week, times cosine of the angle of the water current, or water's vector, and sine of the angle of the water vector. So that's the setup. That's essentially what we're going to do. Now we can replace that with numerical values. We've got 7.0 times cosine 90 degrees, sine 90 degrees, plus the water's vector was 1.5 units in length, times cosine 40 degrees, sine 40 degrees. Now here's where using this setup is really, really beneficial. This is an expression that I can bring to the calculator now, and I can use the calculator to produce a final result. And what the calculator will do is it will take the 7.0 and multiply it by cosine 90. It's going to take the 7.0 and multiply it by sine 90. It'll take the 1.5 and distribute it in just the same way. Now, if the angle measures were nice, we could have done this by hand. In fact, we should recognize that cosine of 90 is 1 and sine of 90 is 0. So 7 times 1 is 7. And 7 times 0 is 0. So the component vector for the ship is 7.0 over 0. And similarly, we would get something for the ocean's vector as well. Now, 40 degrees is not a nice number inside our unit circle, so I can't do this one in my head. But that's essentially what the calculator is going to be doing behind the scenes. And so we'll let it do all of that work for us. I have no problem with you using this tool as long as you understand how to use it and what it's doing behind the scenes. So this would be sufficient evidence for work. Now we'll just go to the calculator and enter it into the machine, and let's see what sort of results that we end up getting. So I'm going to start a calculator page, and I'll start with 7.0, and I'll multiply it by a matrix. Now the matrix that we want is here inside of this button right next to the number 9. And the option we're going to choose is the 4th column, 2nd row, this matrix here. This is going to create an empty matrix that has 2 rows but 1 column. And in the upper column, we're going to call the cosine function and evaluate it at 90 degrees. And we're going to call the sine function in the bottom group and evaluate it at 90 degrees, taking note that my calculator is in degree mode. That's essential for this problem. We'll add to that 1.5 and do the same thing. Now, since this was the last matrix that I used, the cursor does automatically remain active here, and so a shortcut that you can utilize is just tapping the Enter key. That last entry will be reused. And we'll set it up the same way. We want cosine of 40 degrees in the upper component of our matrix, and then we want sine of 40 degrees in the lower component. If I'm satisfied with the setup here, I'll just press Control Enter to produce a decimal result in case it doesn't automatically do that for me. And since we were using 3 significant figures along the way, we'll report 3 significant figures here, 1.15 and 7.96. So I'm using blue ink here, 1.15 and 7.96. And I just realized something seeing this result. I think I announced these 2 solutions backwards when I was doing them in my head before. Cosine of 90 is 0, sine of 90 is 1. So 7 times 1 should have been 7, and 7 times 0 should have been 0. So this result here is, I think, pretty good because it does represent the triangle that's formed by this blue vector that has a width of positive 1.15, so that means it's pointing to the right, and positive 7.96. That means that it's pointing up 7.96 units. And so while this vector is reported in rectangular form, we can very easily work backwards and utilize it to find the magnitude. So the magnitude, and I'm going to use R for this vector because this is the result of the combination of the others. The magnitude of the resultant vector is simply the hypotenuse of the triangle that's formed here. And so we're going to use the Pythagorean equation. 1.15 squared plus 7.96 squared underneath a square root tail. And that result looks like 8.04. So 8.04. And the unit of measure for the length in this case is meters per second. It looks like the ship is moving 8.04 meters per second. Now, truthfully, that's all that this question was asking for, but we might as well just take this one step further and find the angle measure. Since we have the opposite and the adjacent side length, we can use tangent to find our angle. So I'm going to use tangent inverse here of the opposite side length, which is 7.96, divided by the adjacent side length, 1.15. And the result from there is 81.8 degrees. 81.8 degrees. Now, that's perfectly fine. I'm personally more of a fan of using cotangent. That's because the fraction utilized with cotangent is actually written in the same order that our vectors are going to be written in. So we have 1.15 on top and 7.96 on the bottom. And as you can see here, the result comes out to be exactly the same. Now, we have seen examples in the past, especially just last week, where these results differed from one another, and they also differed from the exact solution. Now, as long as the answers fall in the first quadrant, as long as the vector that we're investigating falls in the first quadrant, both will give us the same answer. What you have to be careful of is when the angle measures fall in a quadrant outside of the first quadrant, especially this one in the third quadrant. It's going to take some investigating and interpretation of the result off the calculator to utilize it. The calculator does work just fine. We just have to be a little bit smarter than the calculator and not trust the answer off the machine at all times. So there's a little bit of a investigation that has to go on with them. We'll talk more about those as those issues arise. In this example, we've got an airplane that's flying 5 degrees south of west, and we've got the jet stream wind that's blowing 35 meters per second, 15 degrees south of east. And so we need to find the velocity of the airplane relative to the Earth, so the combined velocity here. To answer part B, discuss whether the answers are consistent with the expectations. Well, I think we can do that pretty easily if we start by sketching a picture. So right off the bat, 5 degrees south of west. Now, west, of course, is leftward, and south of west would be this direction. So 5 degrees south of west, I think we'll go ahead and use 185 degrees on the 360-degree scale. And for 15 degrees south of east, now east is rightward facing, and 15 degrees south of that, I think we'll go ahead and report that as 345 degrees on the 360-degree scale. And that's going to help us with our component computation. Now, as far as a sketch goes, let's see here, 260 meters per second versus 35 meters per second. That means that the arrow that I draw for this first vector, the airplane's vector, has to be a little bit more than 7 times the length of this vector. And scaling on a grid line may not be helpful because these vectors are drawn at an angle. So first things first, let's see, this is going to go mostly leftward and then back to the right. So I'm going to start somewhere over here, and I'm just going to place a mini XY axis on the page here, just so that I can get a perspective for my direction. And the airplane's vector is traveling 260 meters per second, 5 degrees south. So I'm just going to draw it out here. So this is 260 meters per second at 185 degrees. Okay, so that's, south of west, 5 degrees south of west. Then what I'll do is I'll draw another small XY axis right here, and focusing on it, I'm now going to draw my 35 meters per second velocity in my 15-degree angle. So it's got to be a little bit sharper of an angle than the first one that I drew, and it's going to be pointing down and to the right from that direction. So this almost looks symmetric, so that might represent 5 degrees south of east, but we want 15 degrees south of east. So I don't know. It's really hard to tell without a protractor. So I'll just call this the result there. And I'm trying to make that line much shorter than the original, about 1/7 of the size. And of course the result is going to be this arrow here. So this is our resultant that we're after. And I better make note of this. This was 35 meters per second at 340 degrees. So if the mental picture didn't come out this way, hopefully physically drawing this makes a little bit more sense. The airplane's flying in one direction, the wind is pushing pretty much with a lot of force against it, so the resultant vector is much shorter. I would suspect that the airplane does slow down quite a bit. This seems pretty reasonable to me. Not only does that happen, but it's also being pushed off course a little bit. The vector angle for the resultant is more steep than the original airplane itself. Well, as far as the setup goes, we'll use the same technique as before, 260 meters per second times cosine of 185 and sine of 185 will be added with 35 meters per second at the angle cosine of 345 degrees, almost made that mistake again, 345, and sine of 345. And the result that I get off of the calculator here is reporting negative 214.5. Now we should only keep three significant figures. So we'll call this negative 215 and 71.1. And to me that result seems pretty good. It does look like we are moving leftward a fair amount, but what's a little bit concerning is that this result down here reported as positive. Now I'm actually using my handheld calculator off screen, so I can't share the image with you, but I just double checked something and the calculator was set to radians. So I better switch that to degrees and recalculate. Now that's actually a good accident there, because the result, for a moment there, I thought it was pretty spot on. This distance almost looks like 70, and this distance looks like 215, so I'm almost okay with that. But here again, we've got to be really careful with our settings. Now I just re-executed that, and it looks like negative 225 is the result, and negative 31.7 is the result. So now both of those are negative, and this vertical height being 31, I guess is a bit more appropriate than 70 that we saw a minute ago. So if 225 represents essentially the width of the right triangle associated with the resultant vector, and 31 represents the height, we can again find the length of the vector, its magnitude, using the same process. The vector's magnitude is the square root of 225 squared, or negative 225 squared, plus negative 31.7 squared. If you do include the negative symbols, which are not entirely necessary, but if you do include them, make sure you put them inside of grouping symbols like parentheses. But the results always come out to be positive as soon as you square negative numbers, so you can eliminate the negative signs altogether. The result comes out to be 227.2, so I think we'll say that the airplane relative to the Earth is moving at 227 meters per second instead of 260. And again, just for practice sake, let's go ahead and compute the angle measure. Now, tangent inverse of, and we always use our vertical component over top of the horizontal component in tangent. So we want negative 31.7 over negative 225. And so the calculator is going to immediately turn this into two positives, and it's saying that the angle measure is 8.02 degrees. If we use cotangent, the calculator also gives us 8.02 degrees. Now these two will not always be the same. but in this case they are. But in either case, they're both wrong. 8 degrees is pointing this direction. This is where 8 degrees sits on our 360-degree scale. And clearly, the resultant vector is not pointing up and to the right whatsoever. Well, as it turns out, if I show this vector against the original, you can most likely predict what's happening here. The calculator has returned a result in the first quadrant, which it's generally programmed to do, but in actuality what we want is the 180-degree opposite of that. And that's perfectly fine and acceptable because of the limitations of our calculators and the domain restrictions that we tend to ignore when utilizing them. So in either event, we're going to add 180 degrees in this case. We're going to say that the angle of the aircraft relative to the Earth is 188.02 degrees. And to remain consistent with the three significant figures, we'll leave that as 188 degrees. So this video is starting to get a bit lengthy already, so I'm just going to stop it here. These two examples from the physics class do very closely align with the examples in our trigonometry class. The next one takes a little bit of thought, especially since we're going to reference additional functions that we're not going to be talking about in our trig class. So if I end up talking about this particular example, I'll do so on a physics video. For those trig students that were watching this, hopefully this sheds some additional light to our current examples. Thanks for watching.